very happy to have Dietmar Wühler, who's proprietor of a very interesting company in Germany that does camera quality assessment services and reviews and stuff like that. You can mention that if you want. So, very interested in this topic of his talk on noise and resolution and interactions between those and things like that. Dietmar, take it away.
Yeah, thanks very much. Yeah, as Dick said, I'm running an independent test lab in Germany, and we had a couple of problems over the years with the developing technology of digital cameras, and one of the bigger problems we had was noise, and there were two different aspects of that appeared, and one was measuring noise. So we do most of the tests for German magazines or for manufacturers who basically see noise not as a physical effect that is in the image, but something that you perceive in an image and that disturbs it in a way. So they want to have a measure of noise in a kind of perceptual way. The other thing is, the other aspect is that we find many of today's cameras, especially cameras like cell phone cameras with a very small sensor, very small pixel size, there is, of course, a lot of noise in these images, and manufacturers try to get rid of that noise instead of increasing the sensor size, because cell phones, for example, have a limited size that you can carry them in your pocket. So they want to keep the sensor size on a very small level, and then, of course, noise of the signal is more visible. And they try to get rid of that noise using image processing in their cameras. And the way they're doing that, of course, also leads to a reduction of especially something we call texture, which is low contrast fine detail. And I will show you how we tried to find a way to get a method, to develop a method to measure this reduction of the resolution due to the noise, the loss of resolution due to the noise reduction that is computed in these images. So the noise sources we have in cameras is basically the capture system itself. So we have the lens, we have the sensor, we have all the electronics, especially the analog part of the electronics in the camera that introduces a certain amount of noise. But on the same hand, we have something that we call noise adjusters. So every single step in the image processing in that camera adjusts noise in a certain way. So if you do color matrixing, if you do shading correction, all that stuff, you change the amount of noise and the visibility of noise in images. There are different things to measure noise in images, different ways to do it. One way is to measure standard deviation. That's what today's standards that we can find for measuring noise are about. But these standards usually don't address the luminance and chrominance aspect of noise. They also do not address the dependence of the visibility of noise on the different viewing conditions. They certainly don't look at the nonlinear image processing. So noise can be different in different parts of the images, and it can be different on different kinds of structures in the images. And of course, we find quantization limits of the noise measurement, and sometimes we want to have an isolation of different noise sources. So especially manufacturers, they want to know where does the noise that I have in an image come from, and how can I reduce it? And of course, things like compression of images add to noise as well. So even if you look at the high resolution output of the cameras, if you compress these images afterwards, you may add some more noise to that. So let's look at the standard way to measure noise. There is an ISO standard for noise measurement in digital cameras, and that is the ISO 15739, which basically makes use of the target that you see here. So it's basically a grayscale, a circular grayscale, and there are some noise patches in the center here that are used for measuring a standard number for noise that is then recorded or reported as the ISO total noise, which is this one here, which basically is the standard deviation in one of these gray patches. So we analyze these gray patches, calculate the mean, and we calculate the standard deviation, and this standard deviation is reported as the ISO total noise value. And typically from this you compute the signal to noise ratio, and since you can apply tonal correction like gamma curves or similar things to an image, this signal to noise ratio, which would be completely linear, and for a system that has no image processing, is corrected with the incremental gain at the certain position. So we measure not only the signal itself and the noise, but also the incremental gain of the so-called OECF curve, so the optoelectronic conversion function, which describes how luminance is converted into digital code values. Then some people like to report noise in dB, and this is how you convert that signal to noise ratio into dB values. There were some problems with the ISO standard because it didn't really specify how to expose the target and how to compute. It specified how to compute the noise, but it made some assumptions that are not that accurate. So therefore, the standard is currently under reviewing, and there is a draft available already for those who are on that committee. And let me just show you briefly how this is going to work in the future. So this was the former method of the ISO standard. So expose the target in a way that the brightest patch, go back to that target, that the brightest patch here, this one, is just doesn't clip, or we exposed it in our lab that it just clips because it's better or easier to control. The new way of exposure is that we expose the target in a way that the background leads to a digital code value of 118. You might want to ask why 118. So typically what the output of most of today's cameras is images that are encoded in the sRGB color space. And for sRGB, the average reflectance, that is a reflectance of 18%, known from the former photography standards, leads to an L star value in the LAB color space of 50, and this is equal to the digital code value of 118 in sRGB images. So that's why 118 is selected. There's a certain range. I don't know whether the tolerances are fixed now, but it'll be something like 118 plus minus 10 digital code values, something like that. Why do we do that? So in former times, we adjusted the exposure in a way that the OECF curves looked like this. So we had different digital values for the same luminance for different cameras according to their way of doing internal tonal correction. So we got different signal-to-noise ratios for these cameras because we had these variations in the mid-gray where the value, the signal-to-noise ratio value was computed. So changing that to the way that cameras use the 118 digital code value for the background, we will get pretty much the same signal-to-noise, not the same signal-to-noise ratio, but the same signal level for this mid-gray tones. And the noise value then depends on the noise value of the camera. But you can find different cameras depending on their different ways of changing the tonal range. So some of them may have highlight clipping, highlight compression in order to record a higher dynamic range. Some of them might have a steeper value here, but then they will clip in the highlights pretty soon. So this will affect the dynamic range measurements, but it'll not directly affect the noise value measured for these mid-gray values. So we expose the target in this way, and then in order to get to a good recording, we will go to the luminance where the output value, the digital code value of the image is 145. So looking like something here. So we select the digital value of 245, and then we look at what is the related luminance value, and then from there we go down to 13% of that luminance value and record the signal-to-noise ratio. So this is not the OECF, this is a signal-to-noise ratio curve, and we select the signal-to-noise ratio here, and that is the reported signal-to-noise ratio. So that basically adjusts for the different tonal corrections the different cameras do. So this way will lead to more standardized reportings of the values. So this is how the standard is going to change, but we still have a problem that when we look at signal-to-noise ratios, we find the case that we have gray patches with the same signal-to-noise ratios or about the same signal-to-noise ratios we've measured, but as you can see here, completely different perceptions. So this is a higher noise, or this patch has a higher noise perception than the one on the left-hand side. So this signal-to-noise ratio measurement doesn't really relate to what we see in the images. So therefore, we were looking for a way to measure noise based on the human's perception. The first thing we did about that was quite a couple of years ago. We tried to show people that CLAB color space doesn't do the job. So we were selecting colors, added noise to that color, And then we made people look at these colors, and they had a slider to adjust the amount of noise in different directions. So add luminance noise, saturation noise, or change the view, the hue of the color, and found that it was, well, depending on the specific color, completely different what we could find. So the levels for luminance, it was very much the same for all the different colors. But depending on the color, we got different hue angle settings and different saturation settings. And it's not really a uniform space when it comes to the spatial aspect of color and of noise in images. So, but the good thing about this experiment was that we had a set of images with a JND. So the people were asked to move that slider to a position where they just could see the noise in that image. So selecting basically the JND and the just noticeable difference. So we had that set of images, and that was a good starting point for when we found actually a method to measure the perception of noise, to prove that method if it's valid or not, because all these images should lead to about the same level, the same value in this measurement, because they're all on the JND line of it. So there were two different things we were looking at, and one was the visual noise, which currently is an annex of the ISO standard of the existing one. Currently, it's an informative annex, and we also had a look at the SCLab approach that was developed by Wandel and others. And there's a very nice paper on that from Johnson and Fairchild called the top-down description of SCLab. So that basically describes what this algorithm is about. And the basic principle of these models is the same. So if we look at the human visual system, we have an object. We have the eye that looks at these objects. We have the cones that receive it. We have a kind of neural system that works on that, and finally we have the recognition. And both of these approaches work in about the same way. So we have an RGB image. We convert that into XYZ and LMS space, so that basically represents the sensation of the human eye. And then we convert that into the opponent space, so which is one luminance channel and the two chrominance channels. And from the opponent space, we do a Fourier transform. We filter that image based on the contrast sensitivity function of the human eye, and of course that is the point when the viewing conditions come into play. So the contrast sensitivity functions depend on the distance of viewing these objects and resolution, etc. And from there, we compute the image back to XYZ, and then we have the difference between the two different methods. One is converting the image to LUV and computes the visual noise from the LUV image by basically measuring the standard deviations in the three color channels, L, U, and V, and the output, the visual noise output, is basically a weighted sum of these standard deviations for the three color channels. The other thing is the other approach, the SCLab approach, basically converts the the XYZ image into LAB, and then you need a perfect image with no noise, and you need that filtered image. Subtract them from each other and basically do the delta E 2000 measurements for each pixel pair of these two images, the perfect one and the noisy image. And from that you can then derive a delta E 2000 difference image that you can evaluate. It's not a single number on the first hand that's coming out of the SC Lab approach, but you might find a way to come up with a single number. So we just had a basic look at these two approaches, and finally we found that that the visual noise approach is a very good one, and actually that the basic work for that approach was done by Po-Shie Hang from Konica Minolta, and he had a bunch of papers. Unfortunately, most of them are in Japanese, so it's hard to have them translated to understand them. But yeah, it was interesting to look at. So these are the contrast sensitivity functions that we actually used. And of course, although people don't really agree on a single set of contrast sensitivity functions that are used all over, it varies quite a bit. We found a set which is basically the one that is reported in the Johnson and Fairchild paper. That is pretty useful. So this is the luminance CSF, which is a bandpass filter. And then we have the different chrominance CSFs as a low-pass filter. And depending on the chrominance, so this is basically the green-red channel, and this is the blue-yellow channel. There's a difference in perception based on these colors. And we applied this model to our images that we got from the first experiment, and it worked out pretty well. So all the J and E images were on about the same level for the visual noise value that was outputted out of this approach, and well, that was a very nice thing. So we finally think we have found an algorithm that really works. One problem we have with that is that it may need some improvement for the encoding. So we're not really sure if the opponent space is the right one. We may be able to improve the quality of the results, but that needs some further experiments. But for the time being, it works okay for our application. So we do that kind of evaluation for 3 years now, about 3 years now, for all the camera testing that we perform in our lab. And we usually test about like 250 different cameras per year. So we've done it on a huge variety of different cameras so far, and it turns out to be very consistent with the perceived amount of noise that we see in images. In order to make it work, we've implemented in our software that we use for the system analysis, and here you can select the different viewing conditions, which you can choose yourself. These are the 3 ones that we typically use. So one is looking at a monitor from half a meter distance. The monitor has a resolution of 96 pixels per inch. This one is for looking at a small image with 10 centimeters in height, and another set is for images with 40 centimeters in height, so like looking at different sizes. And this is basically the weighted sum, so the factors that we use for that, and these were evaluated by the Konica Minolta guys, and seems to work pretty well. So this is what these curves look like. The interesting thing is you can not only apply it to the noise chart that the ISO standard provides, but you could also do the same kind of evaluation for a target like this, which is basically the color checker SG that you can get from X-Rite. And you can find, for example, with this camera that we've analyzed here, that this camera has some problems in the light red tones with the amount of noise that you see there. Okay, so that is how we measure noise today. Coming to the second aspect that I mentioned, we found that, of course, if you look at today's cameras, the amount of pixels, which we call sampling rate, is not the resolution. The sampling rate of today's cameras do not necessarily lead to better detail in images. And there was a little initiative that I started about 1.5 years ago called 6 megapixel, which is actually not about the number of megapixels, but about the pixel size itself. And the bigger pixels you have, the less noise, of course, you have. And for today's cameras, this is, for example, a 6 megapixel camera. This is a 7, 8, and 12 megapixel camera. And if you look at the details of this image here, you see that there is actually more detail in this image than there is in this image of this 12 megapixel camera. And that is mainly because due to the amount of noise that is in the lower right image, the manufacturer had to do a noise reduction. And that noise reduction leads to a loss of details, low contrast, fine details in images. Similar image, so you see that these are looking a little dark on this screen here, but you can definitely see that up here you see a much higher detail level in that 6 megapixel image than you see in that 12 megapixel image down here, or also the 8 megapixel camera wasn't all that bad, but this 7 megapixel camera wasn't that good. So there's obviously some image processing going on that leads to a loss of fine detail in these images. The problem was that we couldn't find that loss of detail in our resolution measurements. I'll show you in a second how we do the resolution measurements. So doing the resolution measurements a typical way, we got a good resolution value because these noise reduction algorithms that I use tend to leave all the edges, high contrast edges in the image untouched. So they only affect the low contrast, especially high frequency part of it. So our resolution measurements weren't really able to reflect that loss of fine detail. So we were looking for something to describe and to measure that loss of detail. So to do that, we looked at all the different kinds of noise reduction algorithms we can find out there, and there's a bunch of different mathematical systems to do that, like averaging, median filter, Wiener filter, coring filter, wavelet filters. In fact, in reality, most of the manufacturers use a combination of those, and they don't tell us exactly how they do it. That's usually a proprietary thing. They all work in about the same way. So you have an input image, you take the low-pass filtered image, and then you take the high-frequency part of that, you modify it in a certain way, put these two together, and you get an output image. So we tried to find a measure to quantize these loss of, to quantify the loss of fine detail in these images. And in order to do that, we used this resolution test chart, which basically has the sinusoidal Siemens stars that are now widely used and that are going to be part of the revised ISO resolution standard. Then we have a bunch of slanted edges at different contrast levels here. That is the method that's described in the ISO standard. And we've added some noise patches here at different contrast level, which is basically white noise. And of course, we added a gray patch here as well. So we just wanted to have different kinds of structures in there to find out what algorithm is the best. This is actually the software that came out of a study. You can find the detailed study, which is the thesis of a guy called Uwe Artmann, diploma thesis, and we've put that on the website. So if you want to know the details about that, you can download it. And this describes different approaches that we've used to find out about this loss of detail. And these are the approaches. The first one was taking the sinusoidal Siemens star, and that basically creates an empty F curve for that system. And this, as I said, doesn't really tell us the truth about the low contrast fine detail. So if you look at this curve, it doesn't change that much for different sensitivities, and it doesn't really show us the difference for the different cameras. The same thing for the slanted edges. So the edges are usually preserved by these algorithms, and what we find is, of course, there is a difference between the different contrast edges, but they remain basically the same at different ISO speeds with different noise cleaning levels. So this doesn't also doesn't tell us the value that we were looking for. Then, of course, we tried to find out about the edge in a little more detail. So looked at the edge itself and tried to find something about the width find out about something about the width of the edge, but that didn't lead to a good thing. Then we looked at the noise level along the edge, because we found that the edges are untouched by these algorithms. So around this edge, you would find a slightly higher noise level, and if we could find out about the amount of noise around the edge, it may lead us to a value that we were looking for. It gave us some information, but not really the one we were looking for. Then we looked at the noise patches. So this is the white noise patches, and we took a picture of these patches at ISO 100 with one camera and at ISO 1600 with the same camera. And you see the difference here. So you see what happens to the noise, and we try to quantify that using the power spectrum of these noise patches. So we basically did the Fourier transform and then looked at the power spectrum. And this is the power spectrum of the white noise at ISO 100 taken with that camera, of the white noise patches with the different contrast levels. And this is the power spectrum of the gray, the uniform gray patch up here. And with ISO 1600, it was interesting to see, and of course you see it here, that you implement that noise is in that gray patch, and of course the software or the image processing in the camera tries to get rid of part of that. So it's interesting to see that these power spectrums get close to each other, which gave us, which looked at first hand somewhat promising. But we had a problem, so we did that experiment on a bunch of different cameras and found, well, there are some cameras that introduce Artifacts. So you can see it here already in a way. So you see these black spots around here in this noise patch, and there were a couple of cameras that introduced even more artifacts to that, and that of course affects the power spectrum here, and we were not able to differentiate between the artifacts and the white noise of the target and the noise reduction. And that was the problem we had with this approach. So we then looked at a different thing, which we call the grade level co-occurrence matrix. So basically, if we take a picture of a white noise patch, the white noise would assume that if you take one pixel, it can have the code values from 0 to 255. And if it's white noise, you don't know what the digital code value of the neighbor pixel is. It can be in the whole range from 0 to 255. And if it's white noise, it should be in the whole range. And depending on how even the image gets of this white noise patch, you can find that there is some noise cleaning going on in that image. And this is demonstrated here by these images. So if you would have, so these are the code values from 0 to 180. That's what the range is that we show here. But basically, it'll range from 0 to 255. And these also from 0 to 255. And if it would be white noise, you would have a black or dark bluish image with no concentration at a specific position. But at ISO 100 of this camera, you can also see that there is a slight concentration towards the diagonal line. And at ISO 1600, there's a higher concentration, and basically everything is getting gray. You see how this concentrates in the center of this diagram here. The problem is, how do you convert that into a single number? Because that's what people usually want, a single number. What is the loss of texture in the image due to noise reduction? So it's hard to come up with a single number out of this experiment. So that's why we looked at another way, and that's about the same approach. So we looked at the digital code values in here and in here, and we basically used the derivative of that image in order to get rid of exposure differences, etc. And what we came up with was this graph here. So the derivative, the histogram of the derivative of that image should have a Gaussian distribution because of the white noise. And everything, whenever it's not a real Gaussian distribution, we know that it is not exactly white noise that we see in that image. And there is an interesting way to measure that, and that is the so-called Kurtosis value. And you find this Kurtosis value in automatic pattern recognition and these areas of image processing. So kurtosis is already used in some parts of imaging. And we just applied that to this application here. And this is basically the ISO 100 image. The green line you see is from the gray patch that didn't have any noise in there. And the others are the noise patches at different contrast levels. And this is the ISO 1600 image. So everything moves towards the center, towards the 0 here. and the amount of that you can see. For the amount of that, you can see the kurtosis value here.
What's it for Gaussian? Is it 1?
It's 0.
0 for Gaussian?
Yes. So this is basically how it's calculated and how we do that. And this is the formula to do it. So it's basically the fourth power of that image. So it's that statistical value. But it reflects very well how far we are of the Gaussian distribution that should be there. And this is the image that you've seen already with the kurtosis values in there. So that is an interesting approach. And we've done this on variety of different cameras now, and it seems to work pretty well. The only problem we have is, of course, depending on the algorithms that the manufacturers use, they are doing this noise cleaning from a certain contrast level on, and it's the trickiest thing here to select the correct contrast of the white noise to have this affected by the noise cleaning algorithm. So we, in former times, used a contrast that was a little too high, and we're reducing that a little more, and then we will have a very good kurtosis correlation with the degrading of the image. Actually, there was a paper which I didn't include here in this presentation given on the Electronic Imaging Conference that talks about the correlation of this approach and the image perception. And there was this psychophysical experiment done on images that were degraded, and it was combined with the results of the kurtosis measurement. And there's a very, very high correlation. It was 0.99. So you cannot get a higher correlation value for these things. There's one other approach that was presented by the guys from DxO Labs in France, and they basically use the dead leaves target, which is in this case, so dead leaves is the approach. So they took it over from some other applications, and they simply use circular structures at different sizes and different code values and combine these on top of each other in this image. And then they basically do the same thing. They calculate the power spectrum as we've done with the white noise already. And from that, of course, since everybody wants to have a single number, they compute something, and that is the so-called acutance value, which you can see here. So that is also, well, since sharpness as a word is one of the nesses, and it basically relates to the perception of an image. So we wanted to use a different word. Actually, this is coming out of the CPIQ initiative, the Cell Phone Image Quality Initiative. And there they wanted to have a measure for sharpness, and what the idea right now is to come up with the acutance measure, which is basically the MTF curve of a system multiplied with the contrast sensitivity function for a specific viewing condition, and divided by the contrast sensitivity function itself. So it's the kind of filtering that we do for the visual noise analysis as well. And this leads to a single value. And these guys from DxO applied that to the power spectrum which is an MTF coming out of the dead leaves target, applied that to the power spectrum and wanted to have or use that number, that acutance number on the images as a measure for the loss of texture. In order to find out whether it works or not, we took a bunch of cameras and photographed the same scene, as you can see here. So there's a white noise patch on the right-hand side and the dead leaves on the left-hand side. And to show the differences on real scenes and real images, we put a green grass patch over here, some stones over here, some bricks. And let me show you some of the results. So this is taken with a camera that had a low resolution due to a low pixel count, so a low sampling rate. The measure was a low kurtosis value, so it didn't do much nonlinear image processing, but it had a high acutance value, so the sharpness was very good. But it didn't have much texture in here because of the low sample rate, so the low resolution of the overall system. That's what the power spectrum looks like. So it is quite high in the low frequencies and then degrades, but here even at the Nyquist, around the Nyquist limit, you have a certain contrast, amount of contrast visible in the image. This is a different camera that has a higher pixel count, but it was simply out of focus. So as you see here, these are blurry images, which of course leads to a low kurtosis value because it's not a non-linear image processing that was done on this image. It leads to a low resolution measurement using the Siemens star or slanted edge approach. And it also, of course, leads to a low acutance value because it's not much in here. And the out of focus thing applies to the dead leaves as well as to any other edges that are in the image. Oops. Then we found, we applied it to a set of camera at different ISO speed settings. We found a little, it's not a real kurtosis problem here. We found that a higher noise level, of course, reduces the kurtosis value because the noise, when it adds up to everything, that is kind of Gaussian distribution, and of course it lowers the kurtosis. But it also leads to a higher noise measurement in that image. So it's somewhat taken care of by the other measurements. And these have a medium acutance value and an average resolution. A problem with the dead leaves approach is that sharpening, of course, changes the acutance value. As you can see here, so this was taken with a camera at ISO 320, and this was taken with the same camera at ISO 640, and what you can see here is you have a slightly higher noise value, but you also have a significantly higher sharpness. So this is just a sharpened image. It's not that there is additional texture in there, but you have a different acutance value for these here. So the sharpening of the image affects the acutance value. And kurtosis isn't that much different, actually. And of course, you can see that from the power spectrum. So this is the power spectrum of the ISO 320, and this is the power spectrum of the ISO 640. And you can notice that you reach a contrast level of 1.2 here and of about 1.0 in this other image. So that means there's not a difference in texture in that image, but there is a difference in the acutance measure, which causes some problems. So both of these approaches, kurtosis and the dead leaves, are somewhat scale invariant, rotation invariant. But for both of them, you have to carefully select the tonal range that you have in your target. And the dead leaves is somewhat sensitive to sharpening and artifacts that are introduced. So one other aspect I didn't mention so far is, of course, you can vary the sharpness here. But if you have high frequency content in that power spectrum, you also do not know whether this high frequency content comes from artifacts that are implemented or introduced into that image by the noise cleaning, or whether it comes from the real original image. And that is a bit of a problem. So you cannot differentiate between these. And kurtosis, of course, the kurtosis does not really make sense as a standalone value. So you have to look at different values like noise and resolution in addition to the kurtosis value to get the complete image of what happens to texture. But if you do that, it's the interesting thing that the kurtosis only describes the loss of the fine detail in the images due to nonlinear image processing, to noise cleaning algorithms that are nonlinear. And this is indicated here. So if you have a bad sensor and no noise filtering at all, you will end up with a high noise level in that image. You will end up with a typical or good resolution value, and you will end up with a low kurtosis value, which is good. And for the power spectrum, it'll be also a low value. You'll measure a high value for the resolution and acutance, maybe. And if you have a bad sensor and linear filtering, you will get a low noise value, but you will also get a low resolution value because the linear image processing affects the Siemens star and slanted edge MTF. And you will get a low kurtosis value because you pretty much keep the Gaussian distribution of that white noise. But you will also get a low power spectrum. Then if you have a bad sensor and nonlinear filtering, that was the problem that we had. So we got a low noise value, a high resolution value, but we had a loss of texture. So we had to find a method to just measure the loss of texture for this nonlinear filtering, and that the kurtosis does very well. And for the power spectrum, it's a bit of a problem because you're not able to differentiate whether the artifacts, etc., that you have there come from the original or from the image processing. And if you have a good sensor, of course, you get a good value for all these different aspects. Yeah, that's about it, what I wanted to show. Thank you very much. And if you need some additional information, there's a lot of things available on that website. And I'm open for questions.
Thank you very much. So it seems to me that there's a lot of interesting, good points to all these measures. Most of them don't take into account what the target is that you're taking a picture of. That is, they don't try to measure the signal. Reproduction.
Right.
Look at a power spectrum or a noise or some statistic that doesn't recognize what it was they were taking a picture of.
Yes.
Would incorporating that help you make a more meaningful, say, signal to noise where there's really a signal there or something like that?
Yes. On the one hand, if you know the signal and if you would have a signal in these areas, it might help, but it's somewhat difficult to compute and do the analysis for that. So, having that white noise and coming up with this kurtosis is kind of an approach where we basically know what the signal is and what it should be like. We don't know the exact position of each digital code value of the pixels, but doing the statistics analysis on that really helps and delivers the value that we were looking for. Yeah, and for the Siemens star, we do that. So the Siemens star is the best method actually to get the resolution or an MTF curve, the contrast depending on the frequency, because we know for each radius of the Siemens star, we know the frequency that we're looking at, and we're fitting in a sine curve that has exactly the frequency that we're looking at this specific radius. And that way we can get rid of all the impacts of aliasing, etc., at the high frequencies. Yeah.
the same camera, same lab for testing,
Mhm.
but many snaps.
Mhm.
Whether you were getting the same number or were it a varying number?
We're pretty much getting the same number. So it's always surprises us since we produce this as test equipment and also sell it. We have a variety of different labs using the same approach and the same setup. And it's interesting that within the labs we typically have a variation that is of the results that is less than 5%. And in our internal lab, we very often have a variation that's less than 1%, which is surprisingly good for image analysis. And if we have a higher variation, we found in the past that it usually depends on capture specific things, so that somebody has set up the camera in a different way, or somebody was had a problem with things. So, for example, they didn't fix the screw on the camera stand or something like that. So if we find that, and we had a very, very big problem in the past, and still have it, with the DSLRs due to the very, very bad autofocus system that most of these cameras have. So if you shoot, for example, 10 pictures in a row, and you look at the images and the variation of that images, I know why a lot of people are complaining about sharpness in digital SLR cameras. And if you talk to those service guys from Nikon, Canon, etc., it's interesting. About 80 to 90% of all the problems they have is according to sharpness and resolution, so the focus aspect of the camera.
Anybody else? Last call.
And do you have a way to switch off the camera's image processing technology and test it?
For a selected range of cameras we have, yes. So for most of the DSLR cameras, you get pretty much raw images. If you shoot raw and then you process it, for example, with DC RAW, and what you get from there is, the image may have some processing, but all the noise correction, tonal correction, color correction, etc., hasn't been done at that point. No.
Most of the time it's 8 bits, right?
The output images are typically 8 bits. The raw images can vary from 8 to 16 bit, and even higher than that for specific cameras. So since we are also looking into things like cameras for security devices and automotive application, these cameras can have a higher bit depth, even higher than 16-bit.
Thanks again, Deepak.
My pleasure.